Hello and welcome to the Edexcel Further Maths videos for Mechanics 1. This is the collisions in 2D section and this is video 1.5, oblique impact with a moving sphere. So previously we've looked at the direct impact of two particles or spheres. Now we're going to look at the oblique impact of two spheres and we're going to make several assumptions. We made these in the previous video as well. Those assumptions are that the spheres are uniform and smooth, they have the same radius, and that the spheres move without rotation. So here we have two spheres A and B approaching each other in the directions shown. These are both the before directions for these. After, we need to think about what happens after the collision. Now the line of impact goes through both spheres, through the line of centres. And if we think about the impulse that's exerted on A by B is along that line of centres, so A is going to be deflected somewhere off in this direction to the left. The impulse exerted on B by A is also along this line of centres, so B is going to be deflected somewhere this way, somewhere to the right. So after, we can see that A is going to be travelling in this direction and B in this direction. Both of them will be deflected, and deflected means that they're going to change direction. So if we want to find the velocities after the impact, what we want to do is look at the motion that's parallel to and perpendicular to the line of centres separately. And in both cases we need to think about the momentum. Right, so let's start off by looking at what happens perpendicular to the line of centres. So we can see here what's happening before for these spheres A and B, and after for A and B. Now you can notice hopefully that the perpendicular velocity components are unchanged. Okay. There's no forces acting between the two spheres in the perpendicular direction, so it's all happening along the line of centres. So that means there's not going to be any change in momentum for either one, which means that the perpendicular velocity components are unchanged. Now if we look parallel to the line of centres now, we can see the same diagram here. If we know the velocities of A and B before the collision, so the velocity of A and B, then we're going to be left with two unknowns to find, remembering that those perpendicular remain unchanged. So we're going to need to find the velocities of A and B after the collision. We'll need two unknowns for this, so we can apply the conservation of momentum and Newton's law of restitution. So now let's move on and have a look at an example. So we've got two smooth uniform spheres A and B, and they have mass m and 2m respectively. And before they collide, A is moving with a speed of 4 meters per second and B is moving with a speed of 1 meters per second. They're both making an angle of 60 degrees to the line of centres, and the coefficient of restitution E is 0.25. So what we want to do here is we want to find the speed of A and B immediately after the collision. So it's really important to first of all write down what the speeds perpendicular to the line of centres are going to be afterwards, because they're not unknowns. We know what they are because they remain the same. We can also write down here that initially this speed is going to be 4 cos 60 in this direction, and the speed of the second particle is going to be minus cos 60 because it's actually moving in that direction. So we know what is happening before, and we need to know what is happening afterwards. So we want to find the parallel component for A and the parallel component of the velocity for B. So let's have a look first of all at conservation of momentum. So we have m times 4 cos 60 minus 2m times cos 60, and that equals mVA plus 2m VB. Okay, so if we simplify this up and divide through by m, we get that 1 is equal to VA plus 2VB. So that's the parallel component for sphere A and the parallel component for sphere B. Now if we look at the law of restitution, we have got 0.25 is going to be, so the speed of separation, VB, minus VA, over the speed of approach. So we can see that initially we've got this one is moving in this direction with a speed of 4 cos 60, and the other sphere is moving in the opposite direction with a speed of minus cos 60. So in fact we're going to add those together because their speed of approach, they're actually added together because they are approaching each other. They are heading towards each other. So that's 2.5 here. Now if we rearrange our first equation here, we get that VA equals 1 minus 2VB. And when we substitute that in to our law of restitution equation here, we end up, when we solve these simultaneously, finding that VB is 13 over 24 and VA is minus 1 over 12. So in fact we can see that sphere A is going to be moving off in this direction and sphere B in this direction. So now we have written on these parallel components of our speed, and we're now going to calculate what the speed of A is. So the speed of A is the square root minus 1 over 12 squared plus 2 root 3 squared. So that is 3.47 meters per second. And the speed of B ends up being the square root of 13 over 24 squared plus root 3 over 2 squared, and that is 1.02 meters per second. Both of those are to 3 significant figures. Okay, thanks for watching this video. The next one will be 1.6, loss of kinetic energy and deflection during an oblique collision.